Volumes by cylindrical shell. Suppose we take the region bounded by y equals 1 plus x minus x squared minus x cubed, the line x equals 0 and y equal to 0, and we rotated this bounded region about the y-axis. To find the volume of the solids, we slide the solid perpendicular to the y-axis so that the cross-section is a circular disk. The volume of the disk is pi r squared delta y. Thus, the radius is a horizontal line segment, which is x. Because of the delta y, we need to express x or the radius in terms of y, but we were given y equals 1 plus x minus x squared minus x cubed. Isolating x in terms of y will be challenging in this case. Instead of slicing the solid perpendicular to the y-axis, we now slice it parallel to the y-axis instead. The thickness is delta x, and if we rotate it about the y-axis, we end up with a shell. This outer cylinder has radius capital R and the inner cylinder has radius little r. Both have the height of y. The volume of this shell is therefore pi r squared h minus pi little r squared h, which we factor out pi h, and we end up with r plus r times r minus r. But r minus r is delta r, and if we let the average of the two radii to be r asterisk, then we end up with pi h times 2r asterisk times delta r. The total volume is the sum of 2 pi ri hi delta r, where 2 pi is a constant, but r is xi and h is the height of the function f of xi. As n goes to infinity, this Riemann sum gives us the definite integral so that the exact volume is 2 pi. The integral goes from a to b, x, f of x, dx. This is known as the shell method, the cylindrical shell method, where the volume is 2 pi times the integral from a to b of the radius times the height times the thickness, where the thickness is delta x in this case, the height is f of x, and the radius is x. This is 2 pi, the integral from a to b. The radius is, again, r equals x. The height is the value of the function in this particular example, 1 plus x minus x squared minus x cubed, and the thickness is dx. Before we evaluate the definite integral, we will need to simplify this, and then we use the fundamental theorem of calculus to find the antiderivative and evaluate at 0 and 1. To do that, we end up with 23 pi over 30. This is the volume, the exact volume of the solid as the result of the rotation. The shell method should be employed when this method is not easily implemented. In this case, for the shell method, we would need to slice the solids parallel to the axis of rotation instead of the disk method, where we slide the solid perpendicular to the axis of rotation. To remember the shell methods, keep in mind that it is the circumference 2 pi r times the height times the thickness of a particular shell.